Good afternoon. This is Chris Alexander reaching out to you from Magnolia, Texas. And I know we've got lots of pipeline colleagues all over Houston and even some people around North America. Appreciate you logging on with us this afternoon. Hope you are all surviving COVID-19. I know we're all anxiously ready to get out and go to the office and start doing some things. We've got our colleagues on WebEx. We're also doing Livestream after watching our pastor do such a good job, him and our music minister on Sunday. I was kind of invigorated to do something a little different. I think a lot of us are spending time on WebEx or GoToMeeting or Zoom, and it just seemed to be good to do something a little different. So we've got two different platforms running this afternoon. Hope everything works out well. Well, we are talking about full-scale testing today, and we've got a lot of information for you. The reason we're doing this is that we realize a lot of you are at home. Normally would have you come out to our lab and see what we're doing. As most of you know, we have IDT Expo platform and we have meetings and get people together. It's just really difficult to do that right now. And so we appreciate having the opportunity to spend the afternoon with you. Hopefully this is worth your time. If you get a chance, go to advintegrity.com, and when you get on there, you can find our workshops. And Wendy Courtwright, that a lot of you know, is going to be posting. I think actually it's already posted a PDF of this presentation. So if you can do live stream, I think it's probably more fun. I will admit I'm a little tired of looking at everybody's Brady Bunch head on all these conference calls. So you can at least see me moving around, and I can point at things on the screen that it's really difficult to do with WebEx. So this is kind of our outline. I've got a few deep thoughts to kind of get us going this afternoon, talking about why are we going to be talking about testing? What's the purpose of this? Those of you that know me know I love acronyms, and so I've got an acronym for us to kind of help contextualize the role of testing in overall integrity management. And most of you that are watching this today, you're integrity management folks and pipeline operators. We had two calls today, one this morning at 10 a.m. Central Time, and then we have two next week. We've kind of specifically sent all the invitations to our pipeline clients. Next week, we'll kind of open it up for everybody. So this presentation is very focused on just the pipeline industry in general. And we'll talk a little bit about goals and testing. Because you can't come out and see us in Waller, we're gonna do a virtual tour, and we've got a couple of photos of our test setup and what we're doing to kind of give you an idea of the kind of work that we can be doing for you. And then I always love case studies. I always love just the opportunity to talk about, I call them war stories, and things that we do in a test lab and how it ties into pipeline operations. So we'll spend some time talking about that today, and then we'll kind of wrap things up. And you know, I wish you were all in the room here with me. We're actually doing this at our house in Magnolia. We've got we call it the ice cream shop, and we've got lots of candy and stuff in the background. So it's a great place to be able to do videos, and I kind of feel like maybe perhaps you're even here in the room with me. So if you've got questions, the last slide, I've got my business card. Chantz Denowh also kind of helped me in putting the content of this presentation together. He's busy working today, so I get to be the person talking to you. So opening slide, whiteboard. If you are like me as an engineer, we spend a lot of time on a whiteboard. People will call us and say, hey, we've got this challenge. And a lot of what we do starts off on a whiteboard. And so our theme in this whiteboard session is why talk about testing. And I started my career in 1993. I finished up a master's at A&M, and many years ago, longer than I want to admit. And pretty early on in my career, got involved in full-scale testing, and I have always enjoyed it. I've also spent a fair amount of time doing numerical modeling and doing finite element analysis. And so to me, the ideal scenario is when you combine those two worlds. And it's not very often you find companies that can do both. You have some companies that do testing, a lot more companies do analysis, because as you'll see in this presentation today, it can be challenging to set up a full-scale test lab. You have to have the right kind of people. It can be extremely dangerous. We'll talk about safety as part of this presentation. And so it's very rare to find test labs. And so that's why you don't have a lot of people talking about it. And to be honest with you, it can be extremely difficult. And at times it can be a challenge. And you know, as engineers, we scratch our head trying to make things work. The thing I love about testing, and you're hearing a lot about models, and as engineers, we talk about models all the time. Professors, we write equations and we build all these models. I think it's really funny today that you hear politicians and you hear newscasters talking about models. By and large, they don't have any idea what a model is. They're just using it, but it sounds impressive to say, hey, we're looking for we're going to change in slope of the curve. And by and large, a lot of these people didn't even like math in school, but now they're resident experts on the slope of a curve. So anyway, I'll keep my sarcasm to a minimum. But what we do a lot in engineering is we develop models. In the pipeline industry, we develop fracture mechanics models. We have models for dents. We have models for corrosion. And the beauty of marrying all of that with testing is we validate these models. And I think all America is beginning to develop an understanding about why you need to validate models. But what is necessary in order to validate a model is you got to have data. And so a lot of what we're doing in the test lab is we're generating data. And I think probably, I don't know everyone who's on the call, but we kind of saw who accepted a lot of your clients. And we're doing work with you right now, and you understand this language. But for some of you who have never done testing before, this is a whole new world for you. So it's an ideal scenario where we go to a test lab, we destructively test things, we blow things up, we pull them apart, we pressure cycle, we bend things, and we can validate these models because ultimately we want very accurate models so we don't have to continue to run tests. And as I said, I think the medical industry is probably learning a lot about modeling. And as young people coming into the industry, there's going to be a lot of interest on the importance of the accuracy of models because it affects everything that we're doing right now. So I love to read. If you know me, and you've heard me say this before, if I had 48 hours in a day, I would read for 24 hours. Well, Wendy Courtwright and her husband got me Tillman Fertitta's Shut Up and Listen. It's a pretty catchy title. I'm not sure I'd use that in a meeting if I was talking to a group of people, other than it's a great book. And if you know Tillman Fertitta, he's been extremely successful. He owns the Rockets, he owns a casino, at least one casino, and he owns a lot of restaurants. So I don't, in one sense, envy him right now. It's a very difficult, with the economy, it's difficult to own restaurants. But it's a great book. If you get a chance, I know a lot of you have more time on your hands than you probably did 6 months ago. So download it or get a copy and read it. It's got a lot of nuggets of wisdom. So I love kind of deep thoughts, and I've got a couple to share with you today to kind of open things up. The first thing is all models are wrong, but some are useful. And it's a little bit sarcastic, but for people that do modeling work, it's a legitimate hypothesis to assume your model's wrong until you prove otherwise. And it's easy to build a model. It's easy to build Excel spreadsheets and build a model based on some kind of analytic solution. But until you validate that model, you're sometimes guessing at things. And by and large in the pipeline industry, a lot of our models have been validated, and we're continuing to do that. Another quote that I use often is from Ronald Reagan. It's one of my favorite quotes, is trust but verify. Now, he was talking about using that from a geopolitical standpoint, but when it comes to engineering and certainly testing, it's a valid philosophy to bring into every discussion. And then the last thing is kind of a quote. I kind of pulled some things out from Tillman, and he calls it this 95-5 rule. And what he talks about, and he's specifically talking about in restaurants, but the 5% that you do, it's not the 95% that everybody else does. It's that extra 5% that really determines the success. And I think we can say the same thing in terms of integrity management of pipeline systems, engineering in general. It's that extra work that you do that differentiates perhaps what you're doing from somebody else. And I'd like to think that possibly that testing falls within that 5%, that the insights that you get in doing work with us and doing full-scale testing is really going to help you be able to make better decisions moving forward, which is the whole purpose of why we're doing what we're doing. So I love graphs. I think even when I teach Sunday school at church, I've always got to draw a graph. I just think as engineers, we think mathematically, and a graph can say a lot. And so we've got this concept. If you'll indulge with me for a few minutes, I'm going to explain to you what the idea behind this is. And this is the ICAD acronym, and it stands for Inspection, Categorization, Assessment, and Determination. So I realize I'm talking to a lot of pipeline folks. We spend a lot of time working with the inline inspection companies, and hats off to the ILI folks. I've got a lot of good friends in that industry. I continue to be amazed at where that technology is going. I think about when I started working in 1993, the information that we get today, in 1993 we couldn't even dream about it. The accuracy that those tools have in terms of getting things like dents and cracks, and they're continuing to get better. And so that's a very target-rich environment. But what you notice when I've graphed this is I've got risk level here on the y-axis, and then on the x-axis I have increased knowledge. And so to a large extent, where we start in the pipeline industry is we get a bunch of data. So you run a MFL or an EMAT or a caliper tool, ultrasonic, you run these tools through there and you get a plethora of data. And I have a good friend of mine who describes a lot of times all the data that we're collecting as zombies on the horizon. And we have all of these massive amounts of data that we have to make a decision with. So in some sense, if you just stop there, you're like, okay, we got all this data, we're done, you haven't solved the problem. So you're having to make a lot of assumptions, which keeps the risk level high. So the tools are getting better, and we're in a position today where we can categorize different features. And there's a lot of information as our computer technology gets better and we get into an automated process of categorization, machine learning. If you look over the next 3 to 5 and certainly 10 years, these tools are going to get smarter and smarter, and they'll be able to classify these features in different bins, if you will. So that's the categorization process. So why we're here today is we want to push that curve down. We want to lower the risk level, and we want to increase the knowledge of what we're doing. I feel like I'm doing a weather map here. But what you see in the big bubble there is we're talking about testing and analysis. And so what happens is we've got these models, and we develop these models, and the goal is to make the decisions easier to make because we're lowering the risk. So for example, if I've got a crack, if I have a high confidence level that I've measured the geometry of that crack, so I've got the length and I've got the depth, and then I've got a good understanding of the material models, okay, and then I go to the full-scale test lab, I destructively test things either by pressure cycling or burst testing, and I figure out what's the ultimate capacity that pipeline has. I've significantly pushed the curve down, okay? So it's kind of the opposite of what we're doing with COVID. You know, COVID, you're flattening. We want to push it down, and we want to go all the way out to the right so that when we have to make a decision, we make that with as low a risk as possible. And the way that we do that is by combining analysis and testing and making these models get smarter and smarter as we move forward in time. Now, in the pipeline industry, we only have a couple of things that we can do. Once we determine that something is severe enough that it needs to be repaired, we've got a couple of options. And those of you that know me know I love composite materials, composite repair. I kind of eat, sleep, and breathe them. Of course, we're going to talk about them in our case studies. So you can put a composite repair on most of the features. You can put a steel sleeve on it, and that's always a viable option. We've been doing that pretty much since the inception of the pipeline industry. You can put a mechanical clamp. Those tend to be expensive and bulky, or you can cut it out. And so on the remediation side, those are the options that we have. But I think a lot of times we make repairs on pipelines that if we knew more, if we got our increased knowledge, we might not even need to make the repair. So that's a lot of, I want you to think about this ICAD curve as we go through this presentation today, because the goal ultimately is to lower the risk in decision making. So there's a lot of words. I don't like putting a lot of text on slides. It's easier just to talk. But you know, the goal in testing is not just to blow stuff up. And matter of fact, we blew 2 pieces of pipe up yesterday. It's a lot of fun. We do it safely, and we'll talk about that here in a minute. That's not just the goal to destructively test things. The goal is to pull nuggets of information so that once again we make those models smarter. And I think I've highlighted it in green here. This is really very simply the goal. The goal in testing is to help you more efficiently make integrity and operational decisions. And so the insights that we get through testing, you'll see these in our case studies, it provides invaluable information to help you manage that process. So this is kind of a busy slide. It's got a lot of text, but as I was kind of preparing for this over the past couple of weeks, I thought it would be good to kind of walk us through a process that we use to take testing and integrate it into the integrity management program. So the first thing is we look at a feature of interest. And so right now we have 5 or 6 projects going. for operators, and we're specifically looking at a feature. Maybe in one of them we're looking at wrinkle bends, another we're looking at dents, another one we're looking at low frequency ERW, selective seam corrosion. So you have this myriad of features that you have to make an assessment process on. And then at that point, you figured out what the features, how do we need to test it? I mean, if I've got a vintage girth weld and I'm concerned about landslide movement, okay, doing a burst test on that is not overly useful or practical. I need to go to the test lab and apply bending loads. And so we spent a lot of time, and I put a whiteboard up, one of the first slides. We spent a lot of time on a whiteboard designing what this test should look like. And you'll see that in the case studies. I've got 4 case studies that are very diverse. They're doing different kinds of things. They're applying different kinds of loads. And then the big question that we got a lot of times is, do we use real, or do we use existing features that come from the field, or do we have to recreate those? The problem is, most of the time, we don't have all of the features that we want. We have a big project right now that we're doing with PHMSA and PRCI evaluating computed tomography. Idealistically, we need hundreds of hook cracks and low frequency ERW cracks and SCC features. We just don't have those, and the ones that we do, we don't want to destructively test those because we need to be able to use them on the inline inspection side. So a lot of times we have to recreate these features. And sometimes it sounds easier than it really is, and we'll walk through that as we go through these case studies. And then you got to figure out what the loads are. If you've got a gas pipeline system, okay, it's important to look at some cyclic loading, but it's not nearly as important as if you have a liquid pipeline where you're more likely to have aggressive pressure cycling. So those are the things that we look at. Then you design the test program. Some test programs are relatively easy to design from an instrumentation standpoint. Other examples require a lot of strain gauges, a lot of instrumentation. We have a case study that we'll talk about here that was extremely complicated from an instrumentation standpoint. We had to have strain gauges in the right place to capture that information. So super important that you get that done right. And then once you do all that, you got to start the test. And once you start the test, the one thing you want to do, and you probably never think about this if you're one of our clients, is you want to hit the record button, okay? It's kind of like when you're doing a video and you want to hit the record button. And I can't tell you, I've had at least 3 times where my younger daughter has sung the national anthem at a football game, and we get home and we're going to show mom the video, and they're like, oops, dad forgot to hit the record button. So anyway, it's bad enough when you do it for your daughter. It's really bad when you do it on a project. So it sounds trivial, but it's super important that you're watching that. One of the things that we do at ADV and most test labs, you have multiple people looking at things and you're watching over the shoulder, and you just make sure you get those things done right. Then if you got a numerical model that you're validating, that's where you do that. You generate all that data. And then the last thing, which is the whole reason that you hire somebody like us, is you want to take all that information and you want to put it into your risk model and your threat models, and you want to be able to manage those defects more effectively. And so anyway, I know some of you we do a lot of work with. The reason we're having this is just to kind of expose industry to the type of work that we're doing, just so we become an extension of what you're doing. And I think a lot of our pipeline clients that we do work with, they become friends, and I feel like we're kind of an extension of what they're doing. You don't have to have a full-scale test lab like what we're doing. You can use us as an extension. So that's one of the reasons that we wanted to connect with you today. So I had to have 2 equations. I heard years ago a professor said, and he was presenting at a conference, he said, the interest in the presentation is inversely proportional to the number of equations. So I've been in a few presentations, and the speakers got thousands of differential equations, and after about slide number 2, you just lose the audience. But I've got a couple of pretty easy equations. I imagine my 5th grade son could probably do the mathematics involved in these. So what we're going to do is we're going to talk about a safety moment. If you're in the oil industry, almost every meeting starts with a safety moment. I decided to save it kind of for the middle part of the presentation. And we're going to talk about stored energy. And I will admit, when I was at A&M and probably even growing up, other than blowing things up with firecrackers and Roman candles and those things, I never had a real appreciation for stored energy. And I think probably most people don't. So if I told you something had 1,000 foot-pounds of energy, that probably didn't mean a whole lot to you. But if I came up to you and I said, okay, I'm going to take 1,000 pounds, okay, and I'm going to put it on a crane and I'm going to lift it up, and I'm going to drop it from 1 foot, okay? That's equivalent of 1,000 foot-pounds. Now, If I raise it 20 feet in the air, okay, you and I would both agree that you've got a lot more stored energy. And so that, if I raise it 20 feet, that 1,000 pounds becomes 20,000 foot-pounds of energy. And so I've done a lot of drop tests over the years. We did one where we dropped 25,000 pounds from 30 feet. So that's 750,000 foot-pounds of energy. So when we're doing burst tests, we run calculations, and almost everything that we do involves water. We do hydro testing. It's a liquid. It's safer to do. It's a lot easier to do, and you get the same amount of information most of the time that you'd get in a gas test. So we did 2 burst tests yesterday, and the burst pressures were around 4,000 to 4,500 psi. So you run through this equation right here. This is 1/2 p squared V over beta. I know there's at least a few non-engineers on here, so I'll explain to you what those variables mean. P is pressure. And so typically in the US we express that in terms of pounds per square inch. The rest of the world, Americans are the only ones that use English units. We express it as kilopascals. And so you got pressure, V is volume. In this equation, I do it in terms of cubic inches. Beta is a compressibility factor. I think water's like 330,000 psi. If you do hydraulic oil, that's a different number. So you have fluids that have a certain compressibility factor. And so you run through that, and you run through it's not obviously very complicated. And for a pipe, 12-inch pipe that blows up at about 4,000 psi, the stored energy in that sample is about 22,000 foot-pounds. So as I said, we did 2 of those yesterday. It makes a big boom. You want to do it in a stored container, but it's something that you can manage. Now, on a rare occasion, and fortunately I don't have a lot of engineers that ask me this, but every now and then we'll do a lab tour and somebody else say, do you guys burst with water or gas? In one sense it seems like it's no big deal. It's actually that someone would even ask that's a very scary question, because the energy that you have with gas is so much more, such a higher level. So there's an equation here. It's a little bit more complicated. My 5th grader may struggle a little bit more with the math. But you use the same variables. You have atmospheric pressure. And what you notice is I've got an exponent. So we're talking about gas is compressible. And that's the difference between if I'm testing with water, I pressurize it. It's got a little bit of compressibility that I see right here. Okay, this isn't an infinite value. I got a little bit of compressibility. But with gas, I keep putting pressure and pressure. And so I get all of this stored energy. So for the exact same test, if I was testing with nitrogen, the energy that's stored is 330 times more than you would get with a water test. So for example, yesterday, completely comfortable doing a burst test that's got 20 or 30,000 foot-pounds. If we had done this yesterday with gas, we would have probably blown our building up. It's that kind of energy level. Matter of fact, if you express it, I think it's 1.5 million foot-pounds is equivalent to 1 pound of TNT. So I've never blown anything up with TNT, so it's not overly meaningful. But it means a whole lot more to me than saying 7.3 million foot-pounds of energy. So the bottom line is when you do gas testing, you've got a lot more energy that you need to be concerned with. And we've done some gas testing. We did a big gas test on a spoolable pipe about 1.5 years ago. It went very well, but we spent a lot more time calculating energy. And in that situation, I think we were at about 1.5 pounds of TNT. So I had a fair amount of energy, but we did it in a bunker and we were away from it. So anyway, you're welcome. You can download this presentation. You can use that. It's really impressive at parties that you can explain to people that you understand the difference between doing a burst test with a gas and a liquid. So all kidding aside, it's one of the reasons with natural gas that we always treat it very carefully, because you have a lot of stored energy. And a lot of the early research that happened going back even before I was born into the 50s and the early 60s was the concern over ductile running fractures and the amount of energy that you have in a natural gas pipeline. So a lot of that drives what we're doing. And when we're talking about this presentation, we want to do things safely. So we're going to give you a little virtual lab tour since you can't come out and see us at Waller. Those of you that come out and see us, we usually have either Mexican food or barbecue being here in Texas. So you can envision being out at Waller with us. So we started our test lab in 2019. This is what it looked like. And up here on the top left, and there wasn't a whole lot there. It's just a big warehouse, had 2 5-ton cranes, and just a lot of ideas about how we could do things. I don't have a photo of where it is today. The building is completely filled up. We've got load frames, and you'll see those here in the next couple of slides. We got about 4 acres. In the center section, I just pulled this off Google, we got a lot of land, and we've buried some pipe. I'll show you some photos here in a minute. So we've got room to do things. We've also got a pull rig that Rosen has loaned us that's kind of up in the back part of the property. And you know, we've made it our home. We've filled it up. You know, we went, I think when we first started, we had 6 people, and now we've got anywhere from 13 to 15 people in the building. So we've got, good news, got a lot of things going on. This is our pressure test chamber, and Corey Duncan, who's our lab manager, did a great job designing this. And so it's basically just a series of I-beams we welded together. We designed a lid. You notice it's got a dome top, and the reason is that allows us to test larger diameter pipes. I think the largest pipe tested was 25 feet long, 36 inches in diameter. And you button the top. Those of you on WebEx can't see it, but I'm pointing to, we got brackets, and those brackets are held in there. We have pins, and basically when you have energy, that energy has to go someplace, and so it basically goes into this chamber. You can see some lines coming out. We usually have video cameras in there when we're recording. So we use this for burst testing, but we also use it quite a bit for pressure cycling. We have a test starting today that we're going to be pressure cycling a large diameter sample. So that kind of gives you an idea of what we're doing. We have several other chambers where we do burst testing, but this is the biggest one that we've got. One of the other things I talked about earlier is that when you are looking at designing a test program, you need to understand what kind of loads that you get. And so early last year, we had 2 clients. One reached out to us in February, and I think the other was probably in April. And they both said, look, we need a test involving bending. And so one of them was a girth weld. Another program was a program looking at wrinkle bends. And so those 2 features, if you will, the thing you have to be concerned with, if you have an area where the pipeline is going to move, you have to worry about bending loads. And so it's not enough just to do pressure. So we basically built this big bending fixture, and you've got a couple of I-beams. Corey designed this, and Chantz Denowh, who is one of our senior engineers, did calculations to make sure everything worked. One of the things I love about this design is you've got 2 parallel I-beams, and you can drop these hydraulic cylinders down inside the two I-beams, and it allows you to keep the sample relatively low. A lot of the tests that we've done over the past 25 years, even going back before I started my career, when we do bend testing, we got the hydraulic cylinder above the I-beam, and you're bending way up in the air. So what we're able to do is we're able to keep things down pretty low. And what you notice is that we're actually doing these inside. So we're able to move the sample in there and apply the bending loads. So you see a couple that we actually have it disassembled. These 2 hydraulic cylinders each will push about 460,000 pounds of force. So you got a lot of capacity. One of the other things that I put on here is we have a 3D printer. I'm kind of a kid at heart, love toys, and it's neat to be able to print things. And so Corey basically took the same SolidWorks file that we built this frame with and just basically put it in our 3D printer and printed this little model of our load frame, which is great. At some point we'll be able to go to shows and we can take that with us and show people what we've got. The other thing that we've been able to do with that 3D printer is we make a lot of fixtures in the lab. So we'll have an LVDT or a displacement transducer. And a lot of times you just take a piece of wood and drill some holes in it, build brackets. But our engineers actually take SolidWorks files and they'll create a bracket, and then they can 3D print it. It's got threads in it. So we've managed to really do this. I think going forward, 3D printing is going to continue to be a really hot area. And I know some of the oil companies are looking at it to make parts and components, kind of an on-demand manufacturing, if you will. And so we're excited about that. We've actually got some initiatives that we're working with some of the oil companies looking at that technology. So one of the other things that this doesn't happen a lot, but on occasion we're called on to do elevated or cold temperature test. And so we were contacted by an operator who wanted us to do some cold temperature testing. So we basically built a box, and you can see this is a Connex container. We basically lined it. You actually can buy kits and you insulate these containers. I've even seen pictures of people living in them. I don't think I have any desire to do that, but it's a great little test facility. And we have this steel box that's on these rails, and we basically push that in the box. So the purpose of the Connex is not structurally reinforcing. It's merely to provide insulation. And then the steel box that we have, it provides the containment during pressure testing. And so I've got a photo. We cooled the box down. We opened it up. and you can just see the coal that just basically frosted over. All of this assembly right here is we have liquid nitrogen, and we basically run it through, and we just cycle through the test assembly. We get everything cold. So really impressed with our guys that they were able to do this. It took a lot of work. Corey and Chantz both have some experience with cold temperature testing and did a really good job kind of putting everything together for us. The other thing, on occasion, especially with composites, there's always a little bit of a concern at elevated temperatures. So we've done pressure cycling on several projects, and we're getting ready to do another one where we heat the box up, and we have a fan that's basically blowing hot air, and we've got up to about 140 degrees Fahrenheit and heating those composites up. One of the other projects that we're working on right now that I'm really excited about is we're looking at spoolable pipes. And it's interesting, within the pipeline industry, the transmission pipeline industry that many of you are, you might not know much about spoolable. And so there's a whole part of the industry. It's primarily in the midstream industry where you have a very corrosive fluids, H2S, and you don't want to use steel, because if you did, you'd have to have some kind of CRA, corrosion resistant alloy on the inside. And so we're making these spoolable pipes, and so you have a liner, a plastic liner, and then you have either a composite or you have steel that provides a structural reinforcement. So it's a really growing area. And so one of the operators came to us and said, look, we're having some concerns with the connections. We've had some failures and would like to do a joint industry program. And my first JIP was about 15 years ago. It was actually my PhD work at A&M. And since then, I think we put 20 JIPs, and we're working on a couple more right now. And so it's kind of become a big part of my career in bringing people together. This one's turned out to be really successful. We started at the end of 2018, and our original goal was maybe 3 operators and maybe 3 or 4 technology companies. We've got 6 operators, and I think we have 8 technology companies. So it's become a really good program. I don't have a lot of details on it, but I did want to show you this little schematic. So what we're doing is we have a hydraulic cylinder that we basically displace the connection, and we basically displace it, and we clamp down the spoolable, and so we're applying a bending load. And so we just kind of finished our first round testing 2 of the companies. Everything went very well, and we apply a pressure for 1,000 hours, which in the composite world is always a good number. 1,000 hours at an elevated pressure, and then we applied pressure cycles. And so we're really simulating probably 15 to 20 years of service, okay, in a relatively short period of time by applying 100,000 pressure cycles. So it's a good little program. If you're interested, reach out to me and I can kind of share with you what we're doing. But as I said, it's turning into be a really good little project. One of the other things that we have, I did not envision when we first started ADV that we would have this, but is a little Tenius Olson machine. And if you've done any pull test, mechanical testing on steel, you've probably seen one of these and might have even used it in school. So we got one of these, and we have it hooked up to a hydraulic unit, and we actually can apply cyclic loading. And so we use that quite a bit. Here's a little wrinkle section from a wrinkle bin that we've tested. We've done a lot of composite work on it, and it's become really a nice little handy tool. We've got some ideas on some other things that we're going to do in testing composites and other materials. In this slide here, there's kind of 2 areas I've spent a lot of my career. One is composites, the other is dents. And I'll admit, when I was at A&M sitting taking senior design class, I had no idea that all the opportunities that you had in developing some capabilities around the dent area. And I don't even know the number, but probably tested 1,000 dents over the past 25 years. And so if you remember early in the presentation, I talked about we can either take features removed from the field or we can recreate them. I think in my entire career, I might have tested 3 or 4 dents actually removed from the field. So the vast majority of what we're testing, we're recreating them. And so it's not overly complicated, but we have an end cap that we press into the pipe. We pressurize the pipe because what you want is you want the area of the dent to have very high strain. And so we're able to do that by pushing the indenter in. One of the mistakes that I've seen people do when putting dents in is they just push into the pipe and then they pull it out. And all that does is ovalize the pipe. So you really need to replicate, what you're doing. And then we put it in our box. Over here on the top right, you'll see a test that we did end of last year. And we had a strain gauge. And the highest stress area is kind of what we call the halo. So if you were to take a flashlight and you put it on top of a dent, it forms kind of a shiny area. That's the highest stressed area. And so you lay strain gauges, and so what the image on the right shows, that photograph, that crack ran right through the strain gauge. And whenever you have that experimentally, that means that you're measuring the area that's got the highest stress. So as I said, we've got a lot of dents. We're even doing some dent work right now. Most of it involves pressure cycling. To a large extent, plain dents, people aren't overly concerned about it. And we proved that many times over the past 20 or 30 years. If you've got a plain dent, and that's just an indentation of the pipe, when you pressurize that pipe, the first thing that happens is you just remove the dent. And I did a bunch of work with John Keefe in the late 1990s, and we put 25% deep dents into pipe. We blew them up. We didn't have one that failed in the dent. There was always no weld seam or something like that. So anyway, I think most of you who are pipeline operators know that information. Instrumentation. So I just grabbed a bunch of, Chantz and I have kind of worked on this presentation for a while, and so I just grabbed a bunch of images of instrumentation and slapped it on one slide. And instrumentation, in one sense, is kind of the unsung hero in testing, because if you run all these tests and you don't get good data, then you're really limited in how you can pull out that information. So, I've got pressure transducers, load cells, strain gauges, and you can see kind of how a strain gauge is set up. This is a clip gauge that we use to measure deformation in a notch. And really the brains of the outfit in this is the data acquisition system. And so Chantz and Corey and our technicians have done a really good job building a foundation for us with a data acquisition system that not only collects data, but we use it to control things. And like I showed the bending mean, we actually set that up, and we can actually apply cyclic bending loads using all of this instrumentation. So really good stuff. Now, once you generate all the data, what do you do with it? So this is actually a plot that we got from one of the pipe samples. And you look at something like that, even as someone who's a stressologist who spends a lot of time working with stress, this is a very confusing slide. And so we spent more than a week kind of processing and trying to figure out. And I'll show you in one of our case studies how we deciphered what this all meant. But we spend a lot of time when we get data that we don't really feel like it makes sense. We have to go back and really dig into the details. One of my favorite sayings, I probably should have put it on my quote slide, is if you torture the data long enough, it eventually confesses. And a really good engineer will dig into it and eventually understand the mechanics. Kind of throughout my career, my observation of some of the best engineers are those who are really good at analysis and who are really good at testing. Because you go to the test lab and you see how things work, and then you go back and you make your models sharp. So, that's a lot of what we're doing. All of the engineers at ADV, we're actively involved in testing projects. And, it's a lot of fun, but I think it forces us to think at a deeper level when things don't work. And, a lot of you, we're working with you, and you get to come out and see kind of this process that we go through. But, there's times it's very challenging, but I think, as engineers, we're always learning something. So let's talk about some case studies. I know I do a lot of presentations, and I go to a lot of presentations, and I'm always more engaged when people talk about case studies. And when I go to a presentation and I just see a bunch of text on it, you're immediately going to lose me. I know when I go to church and I listen to a preacher preach and they tell great stories, I'm engaged in that process. So these are kind of the stories of at least 4 of the stories of things that we've done at ADV. So one of the things that most of you are familiar with is low-frequency ERW. And we have had some failures in the pipeline industry associated with low-frequency ERW pipe. Without going into a lot of detail, prior to 1970, we used low-frequency instead of high-frequency in the process of manufacturing these ERW seams. So from a testing standpoint, in order for us to evaluate these seams, what we will do is we'll put an EDM notch in the seam, and then we'll do pressure cycling to create cracks. And so what this image shows right here, we've actually etched the surface, and we're identifying where that bond line is. And we want to be very careful that when we put the notch that we are spot on. Because if you're off a little bit, if you do a burst test, you're not getting the true effect of the ERW seam in that. This right here shows how EDM, electrical discharge machining, works. And an EDM will basically, it goes into the pipe and it basically removes material, and you can get a very precise notch, and we'll show you that here in a second. So what we're trying to do is we're simulating features in that ERW seam, because it's very rare that we get pipe that has that in our lab. So here's a couple of tests, a couple of photos of burst tests. And those of you who are pipeliners, if I showed you that photo, within about 3 nanoseconds you could tell me what that was. That's low frequency ERW. So once you start a notch, it just runs. And this one fortunately failed at a pretty high pressure, so there's a lot of energy that drove that. If we'd had a longer sample, it would have kept going. Now on the right there, and I warned you at the beginning, we're going to be talking about composite repair, so we had the same feature in that pipe on the right, and we had a composite repair on it. So that was actually the Atlas carbon fiber epoxy system that Milliken makes. CSNRI is the company now. And we've done a lot of work with that company. They have really solid technology in reinforcing cracks. Now, over here on the bottom left, we've taken a section of one of those notches, and we've showed you the difference between a notch and a crack. And a lot of you know Ted Anderson. Ted's recognized as one of the fracture mechanics gurus, probably internationally. And I remember probably about 10 or 15 years ago, Ted and I were talking. He said, now Chris, when you're doing testing, notches are not cracks. And so this image right here clearly shows you, now we're pretty well zoomed in, but that is a notch that we've made. But until we apply cyclic pressure, we don't generate that crack. And so what makes cracks so dangerous is the sharpness. Now, a notch, if we didn't have a crack in there and you do a burst test, there's actually a thing called notch stiffening or notch strengthening. Sometimes you can actually get higher burst pressures by the presence of a notch if it's properly sized. Once you put a crack in there, certainly in low frequency ERW, and you do a burst test, it's going to look just like that photo there on the left. So a lot of energy driving these things. So one of the other areas that we've got into when you talk about testing, it's validating technologies. And if you go to shows like I do, if you go to the Offshore Technology Conference, you go to the International Pipeline Conference, we've got PPIM, Pipeline Pigging and Integrity Management Conference here in Houston every February. And you walk around and you visit with people in booths. Usually there's a sales guy there, okay? And you're going to ask them a few questions, and salespeople are great conversationalists. They're almost always positive, because if they weren't positive, they wouldn't be in sales very long. And if you ask them, hey, does your technology work? The response you're always going to get is, oh yeah. Now, as the guy who's like the town doctor, okay, a lot of times people bring technologies to us, and they don't perform to the same level that the sales guy is promising. So that's a lot of what we've done in the past couple of years, is we're working with technology companies, we're working with operators, and we're kind of in the middle, representing both sides. And so it's super important if you're going to use a technology that it works, because it's dangerous as a minimum. Sometimes it's very expensive to use technologies that don't work. Well, we're doing some work. It's actually a very large project for PHMSA and PRCI looking at computed tomography. And so there's a company called Inspection Associates here in Houston, and they basically retained us, and we basically made some samples to allow them to see how their technology would inspect. So we took some 12-inch pipe, we put EDM notches with depths ranging from 10 to 40% of the wall, and then if you notice there on the bottom right, they're very thin. And one of the things that we're starting at ADV, we're actually starting a fabrication company, ADV FabWorks, and we're going to really perfect this process and try to get these notches as thin as we can. Everything we're doing right now seems to look really good. So you take these notches and then you pressure cycle it, and then what happens is you create these cracks. And so we'll put a strain gauge across the top. There's also some other tech. We use clip gauge, and we've got another technology we're working on that allows us to monitor the propagation of the crack as it goes through that notch. And what we're doing is, as the strain goes up, we can see that we're getting crack formation. The ideal scenario is we start cycling, and as soon as we have a crack form, we just stop it. And so we know what the depth is. I'm optimistic over the next 3 to 5 years the technologies are going to continue to get better, and we'll get a little bit more precise in this process. But this just shows 3 samples in our boxes we're pressure cycling. So once we pressure cycle to a certain target depth, sometimes we'll run all the way to failure. Sometimes we run out maybe 100,000 cycles, 250,000 cycles. More often than not right now though, we just basically run to a certain number of cycles. Once we see a crack that's initiating, we stop it. And then we let the inspection companies kind of do their thing, and then we break them apart. And so this is just an image of the same notch. So basically the notch is 3 inches long. We split it right down the middle, And in one side, we look down the axis of the pipe, and that's what you're seeing, this, what I'm calling the transverse view. The other image, we basically put in liquid nitrogen and we break the surface open, and that's what I'm calling this longitudinal view. And so if you look very closely, it's got obviously a lot of rust on it, but you can see the outline of where the original EDM notch is. And when you pressure cycle, and if you've done any fracture mechanics work, we talk a lot about elliptical surfaces that are created. And what you notice is that's exactly what happened. If we had continued to cycle, eventually this rusted brown area would have gone all the way through the wall. So what you notice is most of the growth is going radially. There's probably a little bit that's growing axially, but at least with these features, most of what we saw was into the surface of the pipe. So we break it open. It's relatively easy. Once you have it broken open, you can put it under a microscope and you can measure what the geometry is. That's what we're going to compare against the inspection technologies. And so this PHMSA PRCI project I was talking about, the gist of it is we're probably going to make about 90 features, and then we're going to have the features inspected, and then we're going to get them back into the lab and we're going to break them open, and we're going to see what kind of correlation that we get. You know, early on in the stage of a technology, it's okay to be off, but as that technology advances, you want to get a higher level of accuracy. And so this is kind of the images on the right are the ones that we got from the CT, the computed tomography technology. And then the ones here on the left are the ones that we broke apart. John Rickert, one of our young engineers, spent a lot of time under the microscope measuring these features and providing a side-by-side comparison. So that was the whole reason that we did this program, was to validate the CT technology. So this last graph is really the money slide in one sense, is that we're on the x-axis were the features that we actually measured. So we broke it apart and we determined what the geometry had propagated. Over here on the y-axis, okay, is what James Medford at Inspection Associates, what he measured. And so an ideal, this is just called a unity plot, and most of you on this line know exactly what I'm talking about. What you want is you want that data to line right on top of the unity plot. And so I can put error bands and look at statistical significance, and I can have a heyday with all of this data, which is what we're going to do when we do the PHMSA PRCI project. We're going to spend a lot of time looking at the statistics. But right now, when I look at that, I've got a pretty good level of confidence that that CT technology has given me the information that I need. There's certainly some areas for improvement. It's kind of it's a new technology, but I think everything we're seeing so far is very, very solid. Talk about case study number 3. I promise you we'll talk a little bit about composites. So if you rewind the clock to the mid-90s, most of the composite work that we were doing was repairing corrosion, and on occasion we were doing dents. And the first big project I did was for GRI, looking at clock spring, and we're putting a lot of dents in pipe and we're doing pressure cycling. So that's kind of how I cut my teeth in this industry. Very few people today question the use of composites in corrosion in dents, certainly in gas pipelines. Liquid pipelines, because of the pressure cycling, there's some other considerations, but there's very few questions that people ask today. The questions that we're getting asked are, can you reinforce vintage girth welds? Girth welds from the 1950s that have seen significant bending loads. Can you reinforce cracks or crack-like features or planar features? What about leaks? And our brethren in the downstream industry, the composite repair industry, has done very well. They do a lot of leak repair, but they tend to be lower pressure. They're not operating facilities at 1440 psi. They're lower pressure, perhaps higher temperature. But it's a different issue. Our pipeline industries are regulated, and so that regulation has additional oversight. And the other thing is we bury pipelines, and so you don't want to bury problems. So TC Energy funded a study, and I'm able to talk about it because we have an IPC paper that's going to be coming out. I don't have a lot of details. I just want to kind of whet your appetite on the kind of things that we do. So the folks at TC Energy, we started working on this project several years ago and kind of outlined it. And one of the primary reasons that they wanted to do it, we talk about in this paper, is they have small diameter pipe with relatively thin walls, so they're concerned about welding on it, but also you get very severe corrosion. What can you do with it? So we tested all the way up to 85% corrosion. I've never built samples in my whole career this deep. So by the time we machined 85% deep on a 156 wall, there's not much left. I mean, I could take my Aggie ring and bang on it and probably could have just immediately created a crack. So you've got a very thin ligament. We drill holes in it to simulate the leak. And then you can see some of the details. We actually tested some of the systems all the way up to 60 C, relatively high temperature for a composite. We cycled up to 80%. In the US, most of our pipelines, transmission liquid and gas, the maximum pressure we're running to 72%. The Canadians run to 80%. So because it was for a Canadian pipeline system, they wanted to really push the envelope. We did a lot of cyclic pressure testing, and that was part of the program as well. We even looked at surface preparation. That's always a big deal, but if you get 85% corrosion, you want to be really careful sandblasting on that. So, you know, it was kind of a dream in a sense. We got on a whiteboard and we kind of laid everything out, and it took a long time to do this program because of all the different facets. And we even had some that we repaired with shop air. So we had air blowing inside through that hole, and the manufacturers had to figure out how to plug that hole and get a seal to happen. And so really impressed with the two companies that participated. And I'll just give them a little bit of shout out. I don't know if they're even on the call today, but one of them is Western Specialties, and they have a technology called the composite sleeve. And they basically take a steel half shell, just like a conventional steel sleeve that maybe Allen Edwards would make, and they glue it on the pipe so it's adhesively bonded. And so they're able to get a strong bond, and then they put a composite over the outside of it. The other technology that we looked at was manufactured by CSNRI. It's the Milliken Atlas Carbon Fiber Epoxy System, and we've done a lot of work with that technology, specifically looking at cracks. And so anyway, two very solid technologies who did very well in this program. So one of the last case study I'm going to talk to you about is a technology that we started working on in 2018, actually kind of late 2017. And there's a technology called the pressure isolation tools. And so the idea is if I've got a pipeline system and I need to repair a valve or I need to replace a section and it's under pressure, how do I work on that pipeline? I don't want to have to blow down perhaps 25 miles of the pipeline. So there are 3 companies that participated in the study. One is Stats, TDW, and then the Pipeline Pressure Isolation Group here in Houston, that we evaluated their technologies. And the way these technologies work is they put them in the line just like they would a pig, and it moves down and it basically remotely locks in place. And on one side you have a high pressure, the other side you have a low pressure. And so the next couple of slides kind of walk us through that. So we run these tools down, and you have a high pressure side and a low pressure side. And so you run 2 of these tools and you set them, and then in the middle, let's say you have a valve and you blow off the pressure. So in an ideal scenario, I can come in and I can make a cut here, I can make a cut here. I've got the pressure on each side of these plugs, but in between I'm able to do the repair work and do the things that I need. These are used very commonly offshore. Stats and TDW have I think probably a pretty thriving business when they have to go in and make repairs subsea. Subsea pipelines are very different though because you have thick walls. So the concern that we had with these tools onshore, and this was primarily driven by David Zhu with PG&E, was what happens when we have thin wall pipe. And so you have companies like Marathon, PG&E, Colonial, you've got these larger diameter. Onshore we tend to be thinner wall. And so what happens when you run these tools through there, what kind of stresses are you generating in the pipe? So the way we started this thing was finite element modeling. At its core, this was a testing program, but I'll give my hats off to David Zhu at PG&E. He's like, look, Chris, eventually I want to build some parametric models, but in order to do that, we need to build some preliminary FEA models, validate them, and then we'll be able to build this model. So it took us about 2 years, but overall the program really turned out very nicely. So these are what the isolation tools look like. So as I said, TDW Stats and PPIG came over. We had a pipe that was specifically for them, because what happens is when these tools seat, you've got seals and you've got basically teeth that engage mechanically on the inside of the pipe. We wanted to see what effect that would have on that inner surface. So we didn't want to run one tool and then mess it up with another tool. So we literally would take 24-inch pipe, would cut it out. We had a replaceable section, and then we'd bring a new piece of pipe in. What you see with these red dots here is we've got the strain gauge locations. And so we spent a fair amount of time working with the manufacturers of these tools and making sure that we understood where we needed to put these strain gauges. So it was a good example of how the modeling worked with the manufacturer, and then we went to the test lab. If you remember that slide I showed you a minute ago that had curves all over the place, That was associated with one of these projects. And what we basically eventually figured out is every pipe has some level of ovality, and when we run hoop stress calculations, pressure times radius divided by wall thickness, we just always assume the radius is the same. Well, as you go around an actual pipeline, that radius varies. And so the hoop stress changes as you go around the pipe. Now, once you get to a pretty high pressure level, everything kind of normalizes. But when you're putting these tools in, they're generating a little bit of ovality. So fortunately, Chantz spent a lot of time, did a great job really looking at that data, and eventually everything made sense. So as I mentioned, after the test was over, we basically sectioned the pipe. John Rickert did a great job, and you can see we found the areas that we were most interested in where the mechanical seals created these areas of interest. We sectioned them, and we looked at them under the microscope, and John did a great job. And what we basically determined was, yeah, you have some markings that happen, but most of you know mill tolerance is about 12.5% of the wall thickness. We're well below that. So I think even if you had an aggressively cycled pressure system, you're probably okay with features of this magnitude. Now, if you had H2S and you had kind of an aggressive environment, it's something you might need to concern yourself with. So anyway, great program. We're looking at possibly doing some other things, looking at doing pressure cycling. But I think with the price of oil right now, a lot of these more hypothetical research projects probably aren't going to happen. So last thing, this is a slide that kind of got carried over. This is a real world crack. And so what you notice is, unlike our EDM notches that go straight down the pipe, you've got a very unusual geometry. So CT technology is really going to be able to help us understand what these features look like. Okay, wrapping it all up. Well, appreciate you hanging in there. Got basically kind of one more slide. So kind of closing things out, we started last year, kind of looked through all of our books, and we did work for 43 companies that included 15 operators. And most of you today are on this call, you're a pipeline company, and we appreciate the opportunity to work with you. We want to continue to do that. As I talked about when I first started, we just want to be an extension of what you're doing. We're able to do a lot of creative things. I think we can come alongside you and help you solve those challenging problems, and we're doing 2 or 3 right now. They're really a lot of fun for us. It's a valuable resource as you make challenging decisions. I've also done a fair amount of work on projects that involve regulators. And regulators like, as I said in this next to last bullet, they like design performance. And so we can go to the lab and we can destructively test things, and it takes the guesswork out of making these tough decisions. And middle bullet here, technology validation, super important part of what we're doing. And we're going to continue to do that. We're even working with companies to help their technologies get better. And the last thing is give us a call. I mean, we're here to help. I've got my card and Chantz's card, and we know a lot of you. We had a session this morning and got texts and emails from a couple of you. If you got questions, reach out to us. Once things get back to normal, we'd love you to come out and see us in Waller, and maybe even do some destructive testing that you can witness and kind of watch what we're doing. So appreciate you being available. Hope things go well. I think we're all ready to kind of get back to some normalcy, but appreciate the opportunity to spend some time with you this afternoon. Take care and have a great day.